Before you tune the threshold, fix how the model learns the rare class. This is the pattern you'll be able to implement by the end, which compares class weighting and resampling and then selects the option that best improves minority detection. I'm Professor Pi, teaching AI foundations with simple Python. Imbalanced classification is a practical pain. You train a model and it looks accurate, but it never finds the rare positives you actually care about. This happens in fraud detection, medical screening, or spam filtering, where one class is tiny and mistakes there really matter. Success means catching many of those rare cases without triggering a flood of false alarms. At a high level, there are two simple fixes. One is to change the model's loss, so errors on the rare class count more. The other is to change the data so the classes look balanced. Each approach has trade-offs. Weighting nudges the optimizer. Resampling changes the sample distribution. Both can improve recall for the minority class, but they can also harm precision or cause overfitting. We will build a minimal experiment that shows both strategies on the same toy problem. You will see baseline recall, then the effect of class weighting, then oversampling, and finally a small grid search and a fair comparison on a holdout set. That way, you know which approach generalizes before tweaking thresholds. Now we'll create the toy dataset and baseline model. This snippet builds a synthetic imbalanced binary dataset and measures the minority class recall with scikit-learn. The call datasets.makeClassification creates data where class 1 is rare, and model selection.trainTestSplit isolates a test set. We train linear model.LogisticRegression to get a simple baseline without any imbalance handling. The metrics.recall score then focuses on how many minority examples are correctly recovered. The random state values make the split and model stable, so results are reproducible. A low recall here signals the model is dominated by the majority class and often misses positives, motivating interventions like class weighting or resampling. The printed recall shows how poorly the minority class is recovered at baseline. Next, we'll apply loss weighting to the same problem. This example applies scikit-learn's loss weighting to counter imbalance and boost minority recovery. The function classWeight.ComputeClassWeight shows the implied per-class weights under the balanced heuristic, which scales loss inversely by class frequency. We pass class weight equals balanced to linear model.LogisticRegression, so minority errors count more during optimization. After fitting on the same training data, metrics recall score evaluates minority recall again on the unchanged test set. Increasing the minority weight typically raises recall, but may trade off precision and overall accuracy as the model becomes more sensitive to positives. The printed recall reveals how weighting improves minority detection compared to the baseline. Now, we'll rebalance the training data by oversampling the minority. This code rebalances the training data through random oversampling and then retrains a classifier. We split training rows into minority and majority subsets using Boolean masks. The function sklearn.utils.resample duplicates minority samples with replacement until it matches the majority count, controlled by nSamples and replace. We then stack the resampled minority with the original majority to form a balanced set and fit linear model.LogisticRegression on it. Finally, metrics.recall_score measures minority recall on the untouched test set. Increasing the resampled n samples strengthens recall, but can increase overfitting due to more duplicates. The printed recall shows the gain achievable by changing data distribution. Next, we'll search for the best manual weighting strength. This snippet searches for a better weighting strength by cross-validating manual class weight settings in scikit-learn. We create a GridSearchCV over linear-model.LogisticRegression with 3 candidate dictionaries that progressively upweight the minority class. Using scoring equals F1 targets a balance of precision and recall for the positive class, and CV equals 3 provides a stable estimate with stratified folds for classification.
The grid object fits models across folds and tracks the best configuration via grid best score.
Stronger weighting generally pushes recall up, but can reduce precision. The F1 score captures the sweet spot. The printed cross-validated F1 summarizes the best trade-off found on training data. Now we'll compare the approaches fairly on the held-out test set. This example compares strategies fairly on the held-out test set using scikit-learn's balanced accuracy score. We score the original logistic regression, the class-weighted model, and the oversampled model to average recalls across both classes, preventing dominance by the majority class. The simple list and argmax pattern selects the best method and computes a gain over baseline for sanity. Balanced accuracy is robust to skew, so a higher value indicates better minority recall without overly harming majority recall. If oversampling or weighting wins, you can later refine thresholds for your use case. The printed method and score reveal which intervention best generalizes before any threshold tuning. Recap what it is. 2 practical ways to handle imbalance. One that changes the loss and one that changes the data. When to use it. Try class weights first for quick, low-risk gains. And try oversampling when the model still misses positives, or you can afford more training examples. One caveat: weighting can hurt precision, and oversampling can overfit if you duplicate too many examples. Next step, take the winning method and tune a model parameter, such as the regularization strength, to squeeze more precision or recall from that strategy. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.